We all move, every single day. But have you ever stopped to really think about how we describe that movement? I mean, with real precision. How does a physical therapist know if an exercise is actually working or if it's safe? Well, it all starts with learning the language of motion. Let's dive in. Okay, so take a look at these two knee exercises. At first glance, they seem pretty different, right? But for a physical therapist, they're both aiming for the same goal, strengthening the quad muscles after an injury. So how do we actually compare them? How do we know which one's better for a specific person or safer? The truth is we can't, not unless we have a really precise way to describe the movement itself.
To make this a little more concrete, let's meet Sam. Sam's a 20-year-old college golfer, and he's working his way back from a pretty tough knee injury. His rehab program, it's full of exercises just like the ones we just saw. For him, getting this movement exactly right is everything.
Now, we can all see his leg is moving. But for his therapist, just saying it's going up and down isn't going to cut it, not even close. They need to know how much is it moving, in what exact direction, and maybe most importantly, how fast. To answer those questions, we need to learn this language of motion.
In that language, that entire framework has a name. It's called Kinematics. This is a core part of biomechanics that gives us the concepts in the vocabulary to talk about movement with incredible detail.
So what in the world is kinematics? The easiest way to think about it is this. It's the geometry of motion. It's a system for describing the what, the where, and the how of movement. But here's the most important part of the definition, what it leaves out, and that's forces. For right now, with kinematics, we don't care about what causes the motion. We are purely 100% focused on just describing the motion itself. And here's the really cool part. To fully describe pretty much any movement, kinematics breaks it all down into just 5 key variables. Once you get a handle on these 5, you can describe any motion in the human body, from something as complex as a golf swing to a simple physical therapy exercise. So here they are, our 5 building blocks: the type of motion, its location in space, its direction, its magnitude, and finally, its rate. Let's walk through each one, and we'll use Sam's knee exercise as our guide the whole way through. First up, type. And really, motion comes in 2 main flavors. You've got translatory motion, that's just a fancy word for linear. Think of sliding a book across a table, a straight line. Then you've got rotatory motion, or angular motion, which is when a segment moves in a curved path around an axis, just like a door swinging on its hinges. So for Sam's exercise, which one is it? Well, as he straightens his leg, his foot is clearly swinging in an arc, isn't it? That is a textbook example of rotatory motion, and the axis of rotation is running right smack through his knee joint. Next up is location. To describe where something happens, you need a map. In biomechanics, our map is the classic Cartesian coordinate system. You know, the X, Y, and Z axes. This gives us a universal frame of reference for any motion, whether it's up and down, side to side, or front to back. These axes create what we call 3 cardinal planes. The sagittal plane divides the body into left and right, and it's where your front-to-back movements happen. The frontal plane divides you into front and back. That's for all your side-to-side movements. And the transverse plane, which is parallel to the ground, is for all your twisting and turning motions. Let's go back to Sam. His knee is bending and straightening, which is a front-to-back motion. That puts his movement squarely in the sagittal plane. So, check it out. We now know the type of motion, rotatory, and its location, the sagittal plane. 2 down, 3 to go. Our third variable is direction. Now within that sagittal plane, we use some specific terms. Flexion is when you decrease a joint angle. A great example is flexing your bicep. Extension is the opposite, when you increase that joint angle, like when you straighten your arm all the way out. So applying this to Sam, his exercise starts with his knee bent. That's the flexed position. The actual work is happening when he straightens his leg, so he is moving towards extension. You see how much more precise that is than just saying he straightened his leg? All right, variable number 4, magnitude. This one answers a pretty simple question. How much? For rotatory motion like Sam's, the magnitude is what we call the range of motion, or you'll hear it called ROM for short. It's just the total amount of movement, the size of that arc his leg swings through. And we measure this range of motion in degrees. Now, you might hear scientists use a different unit called radians, but in any clinic, you're going to see a physical therapist pull out a tool called a goniometer to measure the exact degrees of movement a joint has. Our final variable is rate. Basically, how fast is the movement? Here we have 2 key ideas. Velocity is just speed in a given direction,
and acceleration, well, that's when you hit the gas or the brakes. It's any change in that velocity. And this isn't just some boring physics concept. For Sam, this is absolutely critical. A slow, controlled velocity is essential for a safe recovery. If he moves too quickly with high acceleration, he could very easily re-injure himself. So controlling the rate of motion is a massive part of his therapy.
Okay, we've covered all 5 variables. We've got all the pieces. Now, let's put them all together and create a complete, precise, kinematic description of what Sam is actually doing.
And there it is. This is the power of kinematics. We went from a really vague, he straightened his leg, to this incredibly detailed description. A therapist can now set a crystal clear goal, like achieving 90 degrees of rotatory motion in the sagittal plane, and then track that progress with real data. This is how you design a rehab program that's truly effective and safe.
So why do we go through all this trouble? Why define 5 different variables? Because this level of detail, this is exactly what separates a generic workout from targeted, effective physical therapy. And understanding kinematics isn't just for scientists in a lab. It's the shared language that lets physical therapists, athletic trainers, and strength coaches all communicate effectively. It's how they can accurately assess movement, prescribe the right exercises, and make sure an athlete like Sam gets back on the golf course safely. There's a quote from the source material that just sums this up perfectly. It says that to really understand how the body works and what's going on when it doesn't work, you first have to understand the physical principles that govern it. Kinematics is that first foundational step.
But this leaves us with a really fascinating question, doesn't it? Remember how we said kinematics describes motion without thinking about the forces? We've totally mastered the how of Sam's movement, but what about the why? What forces from his muscles, from gravity, from the machine itself are actually making it happen? Well, that's a topic for another day.